On the first problem, we're given that f of 5 equals 12 and f prime of 5 equals 1.4. And we're asked to do various things with that, but in the first sentence we have enough information to begin sketching a picture. The picture, then people were able to do this once I said draw a picture, but in class nobody drew a picture. You draw a picture, you got 5 here, you got 12 here, you got the point 5, 12, and that's on the graph of f of 5, of f of x. F of 5 equals 12, so we have the point 5, 12 on the graph. Now, there's a point 5, 12. We also know that there's a slope of 1.4. Now, a slope of 1.4 means every unit you move over, you move up 1.4. Now, you can find a common denominator or whatever, multiply 1.4 by something that gives you an integer that gives you an integer. And you can easily figure out that if you move 5 units, you're going to move up 7. So you're going to move up 7/5 as much as you move over. So if we move over some distance here, we move up 1.4 times that distance. I might have that a little too steep. Of course, my scale is not completely consistent. If this is 5, well, it's very plausible that that is 12, but we know on a hand-drawn graph that it won't be exactly so. All right, so now at this point we have just this picture. And if we enlarge that picture, I'll kind of draw it over here. We have the point 5, 12, and we have slope 1.4. This incidentally gives us a tangent line. It's a tangent line and it has an equation. And we've, earlier in the course, been over how to do the equation of a tangent line. Basically, you have a point and a slope. You find the graph or the equation of a line through that point having that slope using the methods of review chapters. So you can do that. That's not what we're going to do in this case, but that's another way it would have been possible to approach the problem. Okay, now, next question is you're asked to estimate the value of the function just based on this information, and ignore this curly squiggly line here, and we'll talk about that in a minute, but that line isn't even there under these assumptions. You're asked to to estimate the value of the function when x equals 5.6. based only on the information that you're given, because you're given no other information, no graph, no nothing. Okay, so how are we going to do that? Well, if this is where x equals 5.6, excuse me, and this is where x equals 5, let's draw the vertical line x equals 5.6, the vertical line above 5.6 on the x-axis. Now, that line goes up here and intersects the tangent line at a point, and that's the point I've marked in purple. It's kind of small, but there it is, and we're going to have an enlarged picture of it. Actually, now that we have this point, we have the point 512, our original point, our new point corresponding to x equals 5.6. That new point lies again on the tangent line at x equals 5.6. So if I enlarge, well, I can draw a small triangle here. Okay, I can draw a fundamental triangle involving the original point 512 and the point at which the tangent line intersects the vertical line x equals 5.6. Now, here's a bigger picture of this. Okay, first of all, we have this point with its coordinates 5, 12, and we have this point that I've marked with an X that matches this point here, and that's the point on our tangent line. Now, there's a 0.84 written here, but we don't yet know how we obtain that, or maybe you do know how we obtain that. But the thing that we can say is we have this triangle. What do we know about the triangle? What do we know from the given information about this triangle? Well, it lies on the line x equals 5.6, and this one is at 512. Well, then this point is at 5.6 something, which means that this side is 0.6. This leg of the triangle is 0.6. 5.6 minus 5 equals 0.6. And it should be clear that between 5 and 5.6 is 0.6, and that this line is parallel to this projection line, so that this distance in this small triangle is 0.6. The slope we know to be 1.4. Now, what do we know about the slope? Well, slope is rise divided by run. And when I pose a question, you should be pausing and answering that question in your own head before you listen to my answer. Otherwise, you're passively observing, not actively learning, and you're getting through the video more quickly, but you're not learning much. Okay, if you're just observing, you're not learning. You need to be active. You need to keep stopping and thinking ahead and answering the questions that I pose. Okay, well, now, back to this. We know that this side is 0.6. It runs from x equals 5 to x equals 5.6. Slope is 1.4, and slope is rise divided by run, so that the rise is the run multiplied by the slope. And we then multiply the run 0.6 by the slope 1.4 and find that the rise is 0.84. So we have this 0.84, and it didn't come out very well when I tried to write it. There's a bump on the blackboard, and I'm a little hesitant to try to make this any better, but let's see if this makes it a little clearer. Actually, I think that helped. Okay, so this side of the triangle is 0.84. Well, what's the coordinates of this point? Again, that's a point where you should stop, pause, and answer the question yourself. Well, here the coordinates are 5, 12. We move over 0.6 and up 0.4, so the coordinates here should be 5 plus 0.6, 12 plus 0.84. That's 5.6, 12.84. That's all actually quite a simple application of the fundamental triangle, which was introduced some time ago, and which I really advocate that you really master. You really have to know everything about it. How do you find the midpoint? How do you find the rise given the run and the slope? How do you find the slope if you know this side and this side? How do you find the midpoint? How do you find this side if you know the rise and the slope? You should have to be able to do all that. It's really essential to understand this fundamental triangle and see this as another application of the fundamental triangle. Okay, well, having worked through this example in class, people had very little trouble working through the other two examples. So be sure you really lock this in. And then, you know, we did another thing now. Here's the calculation for the second point. We're trying to predict at 5.03, and following the same reasoning, we find a run of 0.03, a slope of 1.4. I didn't write that down, but we know that. We multiply the slope by the run, we get the rise 0.042. So if we start at 512 and move over 0.03 horizontally and then 0.042 vertically, we get to 5.03, 12.042, and this is our estimate of the value of the function for x equals 5.03. Knowing nothing else about the function, only its value when x equals 5 and the slope of the tangent line when x equals 5. Now, I asked people to sketch the tangent line and the point, and a point, a curve, such that the given point, the 512 point, was the point on the curve. Now, I saw a couple of good graphs of this. Then I saw about 3 graphs, and I'm afraid there might have been a little cross-fertilization because it was 3 people sitting in a row. We had the point 512 here, we had this point here, we had this little triangle, and we had something like this. Okay, now I didn't quite hit it. My point of tangency looks like it's there instead of here. But the people that drew this did a pretty good job of making this the point of tangency. Okay, they had a curve that was nicely tangent at this point. However, that's not the point. This is the point at which the tangent line occurs. This is the point where the slope of the tangent line is 1.4, not at this point. So the graph should have been kind of like so, and I didn't do a very good job of hitting the tangent there either. Now I drew another one like this. This is the point on the curve, not the point where we approximate the curve. This is on the curve. This is our point 512. So it's 512, not 5.6, 12.84. That's not on the curve. It's not on the curve. But probably close, depending on how big the second derivative of this function is. The second derivative tells you how fast this thing curves, which is going to tend to tell you how fast it curves away from the tangent line. Okay? But this is not the point where the curve is tangent. This is the point where the curve is tangent. Okay? So we want to be clear about that. But again, people did a good job of understanding what a tangent was and so forth. Again, I'm a little concerned that three people had the same picture in the same wrong place. So I'm thinking somebody's being influenced by someone else. So you want to be careful about that. Show me what you're thinking. I'm not going to get mad at you. I'm not going to give you a bad grade. If you're not thinking right, I want to be able to address it. And we did get a good example of not quite correct thinking by, hitting this point instead of this one. But generally, make sure that I can see what you're doing rather than what somebody else is doing. Okay. And if you got no clue, leave it blank. I'll know you have no clue. We'll talk a little more. What we see from this kind of picture is that the further you get from this point, the further the curve is away from the tangent line. Because if this thing has a curvature, it's going to be curving away from the tangent line. If you're really close to the point of tangency, it's not going to have had time to curve very far away. If you're further from the point of tangency, then your curving away mounts up. Now I drew this curve. I didn't say this was necessarily a function, although I did use function notation, so implicitly it should have been, and I probably shouldn't have had these loops in it because the horizontal line test fails miserably. Also here, the function kind of doubles back on itself, so you can do, I said a horizontal line test, vertical line test. Vertical line test would fail in parts here also, although not at the point here. And at the point of tangency, the function behaves just fine. It behaves like this. Okay, well, hopefully that clarifies the situation, and this situation leads directly to consideration of the differential. The differential just says that, okay, let's assume that we have constant slope, and what's our estimate? Just what we did here, but in slightly different notation.